Okay, 5.3. So what did we talk about yesterday? Just so we can kind of set the stage. Linear regression. And we created a regression line. But then that's kind of where we left it. Just, hey, here's how you create the line. Here's how you get the slope. Here's how you get the intercept. Okay, we're done. Now today's going to be spent looking at how well does the line actually fit the data. Is it a good fit? Is it a bad fit? How well does it fit it? So I'm going to do something different than what I did with third period. Okay, I'm going to do something a little bit different, I think. Yes. Okay, while I take this call, I want y'all to go on and go to the deer mouse example and put those numbers into L1 and L2 in your calculator. Mr. Full-time. Yes, ma'am. You can out now. So we're putting the x's in L1, y's in L2. And if someone needs a calculator, they can borrow mine. I'll give y'all a second to finish entering them, and then we'll actually lead into it like we're supposed to. Yes.
The question I had asked you last night, I wasn't able to find where I was talking about that in the video. So I was wondering, you know, like, give me like a quick, like if you had like in your head, like a quick one on how to get like the critical value.
I would have to reference the assignment.
Whenever there's possible time.
Okay. Okay, so Hopefully y'all have y'all's data entered. I have mine entered. Let's actually lead into it like we're supposed to. So once the least squares regression line is obtained, the next step is to examine how effectively the line summarizes the relationship between x and y. So there's three important questions that we have to ask and that this process will help us with. First question, is the line an appropriate way to summarize the relationship between x and y? So where that comes into place, let's say we have just all this data that's kind of curved like this. Would a line that goes like this be considered appropriate? Probably not. So that's our first question. Second question. Are there any unusual aspects about the data set that we need to consider before proceeding to use the line to make predictions? So if I have, like we kind of rushed through at the end, but if I have all these points down here, maybe kind of go like this, and then I have a point down there. What's this point going to do to the line? It's going to kind of pull it down that way towards it. So that point would be what we're going to talk about today, called an influential point. Third question. If we decide to use the line as a basis for prediction, how accurate can we expect the predictions to be? So towards the end of today, we're going to see that, let's say the line only explains 32% of the data. Should we expect much accuracy from our predictions then? No. Not if it's only capturing 32% of the relationship. So those are the questions we're going to answer today. We're going to look at graphical methods and numerical methods to answer these. So we have this deer mouse example that y'all hopefully entered the data for in the calculator. In a recent study, researchers were interested in how the distance a deer mouse will travel for food, which is our y variable, is related to the distance from the food to the nearest debris pile. Distances were measured in meters, and Minitab was used to fit the least squares regression line. And they give us the partial output. And we're going to see this now. We're also going to see it at the end. So from this output, this is where we kind of left off yesterday, how to read the output. This first piece where it says constant and then the coefficient is negative 7.69, that's our y-intercept. So when you're reading this computerized output, if it says constant, that's your y-intercept. This 3.234, think of this as like your x right here. So this would be our slope. So how can I write an equation then with these two values?
When you do the y y hat equals x plus bx.
Yep. So y hat equals negative 7.69. That's right. That's our regression line. Negative 7.69 plus 3.234x.
The regression line is y hat.
That's right.
Is that always what it's gonna be?
Yeah. So now they ask us to plot the data, including the regression line. So here's where our calculator comes in. Just to kind of review what we talked about yesterday, let's get the calculator to not only create the plot, but do the line as well. So let's go to run our regression. You go stat, calc, and then let's see, we need option 8.
Where are you going to draw the scatter plot when we get it?
Yes. Scatter plot and the regression line. And then we want to store the equation into y1. So vars, function, and y1. And then when we calculate it, it will automatically store it into y1 for us. Now I want to plot it. But I need to make sure stat plot is turned on, and it's not. Let me turn it on. Now I should be able to plot. So on the bottom of page 11, I'd like you to draw the scatter plot and the regression line on the plot. Okay, anyone still need time to get the scatter plot drawn? Okay. So the vertical deviation between the point and the least squares regression line is called the residual. We kind of did a little bit with this yesterday when we were creating the line. But this distance is called our residual. So if a point is above the regression line, then the residual is going to be positive. If it's below the line, then our residual will be negative. Not right now, we're not. So we're just saying we're just talking about the distance from each point to the line itself.
Okay, so I don't want to probably
That's right.
Okay.
Yeah. We're about to find the residuals, but right now we're just talking in general.
Got it.
And this is on the top of page, there's 2 blanks on the top of page 12 that we're filling in. Yeah. So let's look at it. If you haven't already turned to page 12, let's turn to page 12. So above is positive, below is negative. The residuals are calculated by subtracting the predicted y from the observed y. And I know it's kind of hard to see. So in that little blank space below that sentence on your notes, but before the 1 and 2, our formula for getting the residual is that the residual equals the actual y minus the predicted y. So y minus y hat. This is another, just putting it in words. This is actual minus predicted. So there's 2 steps here. First, we have to find the predicted value. Then we'll subtract to get the residuals. So instead of having us all go through and do the whole table, I'm just going to kind of go down the row and have y'all just do a certain point. So Riley, if you'll do that first point on that table, find the predicted value, and then use that to get your residual. KJ, if you'll do the second point on the table on page 12, find the predicted, and then find the residual. Julissa, the third point.
The distance, that's the x, right? On the table.
Yeah, distance from debris is your x. Brandon, if you'll do the fourth point. Rosie, the fifth point. Justine, the sixth. Isaiah, the seventh. Shatara, the eighth. And let's see, how many does that leave me with? And then AP, y'all can just duke it out over who wants to do the 9th point.
What are we round to?
Let's do 2 decimal places. So the way you would do this is use your regression line that we found on the previous page to get the predicted. So y hat equals, what did we say it was? Negative 7.69 plus 3.234x. Yep, your x would be your first column right here. That's right. 2 decimals, yes. And then once you get your y hat, subtract these 2 columns. Do the second column minus the third column.
And how many decimals do you do the y hat?
Let's do 2 decimals. Hey, so Riley, what'd you get for your point?
For my y hat?
Yes, the y hat.
For my y hat, I got 14.75. And for my residual, I got negative 14.75.
Okay. And KJ.
I was confused.
Okay, I had several saying that I've kind of confused them. So what part are y'all confused at? So I don't want y'all to be confused. What's that? How did we get these numbers?
Oh, you just took the y value, you put in like 9.6, you put 9.6 in, and subtract the y value again from that.
So this equation we actually got from the output. Let me back up. We got from this output. So, do you understand how to get this part? We're just using this same equation. Yep. And that gets you your predicted y.
Alright, is the predicted distance travel 9.22?
Yep.
And then the residual is 3.09.
Would be positive 3.09.
Right.
So we want to do 6 minus 9.
No, maybe.
So negative 3. Negative 3.99, okay? Riley, did you also get?
Yes, I got that.
Okay.
She got the y hat as 9.16.
Yep.
The residual as 2.13.
That's right. Okay. Brandon?
On the predicted, I got 15.27,
Yep.
and then on the residual, I got negative 0.92.
Negative 0.92, okay. Okay, Rosie.
The predicted, I got 18.7.
Yep.
And then for the residual, I got negative 6.67.
That's right. Justine?
10.10.
10.10. And then for the residual?
12.16.
That's right. Okay. Isaiah?
Oh, wait.
Okay. And then Satara? $4.58. Okay, and then AP, what y'all get? 22.58. 8.07. Okay, good job. Now, did anyone figure out that you actually didn't have to calculate them?
There was I thought about that, but I went ahead and it's like, the quick calculation of the table, right?
I have the table printed on the very next page. We did good. But we know how to calculate them now, don't we? We know how to calculate them now. So our values may be a little off from the table, but that's okay. Mm-mm. Okay, we did that. Okay, so if we add up all of the residuals, add up that far left column, what do y'all get? Add up all the residuals. It does. Yep. You think it'll always equal 0?
Yes.
Yes, it will. So that's what goes in that blank. Will the sum of the residuals always equal blank? Always equals 0. And then your answer would be yes. Okay, so let's talk about, we calculated the residuals, but let's talk about their importance. So for a residual plot, it's a scatter plot of the x and residual pairs. For instance, on our chart, the first pair that, like the first point using our chart would be 6.94 and 14.76. We would plot that point, sorry, negative 14.76. Oh no. 6.94, negative 14.76. Then we would plot the point 5.23 and negative 3.10. So it's a scatter plot of those points. Or you could also do the residuals against the predicted y values. So instead of the x being here, y hat would be there. And the purpose is to determine if a linear model is the best way to describe the relationship between the x and y variables. So our goal is for it to look just like a random scattering of points.
So if it looks like positive or negative, then it's not good.
If there's some kind of pattern, that's not good. We just want it to be random.
That means you need zero, or that just means it's a bad thing?
That just means that a linear model wouldn't be appropriate. So let's look at those two plots on the bottom of our page. So the first one, you see how they're kind of all scattered about just randomly? This shows no pattern, which means a linear model is appropriate. But if we look at the other one, see how we kind of see a curved pattern going on here with the residuals? That tells us that a linear model is not appropriate. Now, we're not going to worry about this one in this class, at least not right now. Well, not that, but there's actually a third shape you would want to look out for. You don't have to put this in your notes unless you're like, yeah, I want to know extra. If there's one that has like a, you see how these kind of, if you were to draw lines, they would kind of almost have a wedge shape here. That's another one that technically would be cause for alarm. I can't remember exactly what that shows, but that does show something is going on with the data. So that's going well beyond this class. But if you're like, yeah, this is kind of interesting, that's another pattern that you would need to kind of dig into the data to find out what's going on. Okay, so we want to use the values in the table to create a residual plot for the data set. And then, using that plot, state whether we think the linear model is appropriate. So there's a couple of different ways you could do this. One way is just to draw you a plot on your paper. This column is your x. Come on. This column is going to be your x. This is going to be your y. If you're like, I don't want to do this by hand, plug this into L3 and have it create the scatter plot for you. So I'm going to do that real quick because I don't feel like doing it by hand. You can do it however you want. I'm going to just throw them into L3. Yep. Leave L1 and L2 alone. We're entering in the residuals. Yep. Okay, now when we do our scatter plot here, let's go to second and y equals, which is our stat plot. So if you can't, you're like, wait, where's that? Look for my mouse up here on the screen. If you forgot where that button's at. So this top one, second, and then this button. Now, yes, plot one is on, but my y variable needs to be L3 in order for this to work right. Y variable needs to be L3.
The second three.
Second, yep, and pick L3. So what this will do, the x-axis stays your x-axis, and then your y-axis is now your residuals, which that's what we want. So then go to zoom, zoom stat, and boom, there's our, that line I don't want. Let me delete it. Oh, you know what, just leave it there, ignore it. What that is, that's our regression line, but right now it's kind of pointless. So just ignore it. Thank you. Ignore that line. But there's our residuals. So now sketch that at the top of page 13. And then what do you think? Does that look random for the most part? Yeah, I'd say it's pretty random. I'd say it's pretty random. Okay, so I'm going to go back to the PowerPoint. So since the residual plot shows no pattern, a linear model is appropriate for describing the relationship between the distance from debris and the distance a field mouse will travel. You can, or you can just summarize it and say no pattern visible, linear model appropriate, something like that.
So if there is a pattern,
You don't really want any pattern at all. Even if it was linear pattern, you don't want any pattern for your residuals. That means there's something going on in the underlying data. Okay. Now they ask us to plot the residuals against the predicted distance. So residuals against y hat. I'm not going to have y'all do this. I'm going to say, hey, here's the graph, and then I want you to sketch it in your notes. That way you have it for reference. So if you were to sketch it, that's what you would get. What do you notice? They're both kind of random. Let me put both graphs up there. It's almost the exact same graph. Except our original, this is the original graph, or this is the one where we have x on the x-axis. This one is y hat. So in both cases, the residuals are on the y-axis. This one, though, has x. This graph has y hat. So residual plots can be done using either your x values or your predicted y values, and you'll still get the same result. So you don't have to, I don't want to say you don't have to do it a certain way, because I mean you have to pick between those two, but it doesn't matter which one you pick. You want to do your predicted, or if you want to do the x, it'll still give you almost the same pattern. Okay, so if you've gotten that written in, well, I'll wait for a second. Yeah, if you've gotten that written in, I want you to do a regression on that black bear example. So put your data into X and Y. You can delete it. And it may be quicker, instead of undoing everything we've done, just reset your calculator. Because you'll have to remember to go back and change stat plot back to L2. Okay, so I'm gonna, while y'all are putting the data in, I'll put the data in as well. Yes. Once you get your data in and you run the regression, all your scatter plot in there on your notes, please.
Is there a number with the residuals on that list?
I do not on this one. So when you when you did your scatter plot and got your regression line, did it look like mine up on the screen? Yes. If it didn't and you want me to look at it, let me know and I can come look.
So do we
Yes. Sketch the graph and the scatter plot and the regression line. Okay, so do you notice anything unusual about this data?
There's not one point of way out there.
It's got one point way out there. And that one point is the point 28.5 and 62. So on the top of page 14, you can note that you have one outlier. So these questions that I'm going to ask y'all about this graph are on the top of page 14. So yes, we do notice something. What do y'all think would happen if I took this point away? Slope would be steeper, yep. So if I take this point away, wait, there's my line. Went from there to there. I thought it would be steeper as well, yep. I
Why does it
figured.
make it steeper?
Why does it make it steeper?
Because it takes, like, that's like, it's like going by like the average of the extra line.
Yeah. So
Oh, we could make it shorter.
that's right.
I was thinking about why. That's why I was like,
Yeah. Yeah, we're removing this x, so this is our true line without that points here. If you add it back down here, that's pulling this tail towards it. I don't know why my board is doing this little weird stuff. But yeah, we don't have that point pulling us down anymore. So the line would change. This one point is what we call an influential point. Because it affects the placement of the least squares regression line. So we can find those points doing the scatter plot. We can also look for them in the residual plot. So on the residual plot, you can look for isolated points or patterns that indicate potential problems. And then ideally, the points should be randomly spread out above and below 0. So you don't want to have your residual plot like this, and then all your points are down here. Something's going on there. Why are we... Hang on, I just had to forget for a moment. Why are we over predicting everything? If they're all below 0, why are we over predicting it? Something's going on there. So that's kind of what this is saying. So if our residual plot was like the one pictured, notice there's no systematic bias. We're kind of scattered randomly all in here. We're scattered above 0. We're scattered below 0. We're just all over the place. So if we're above 0, this means we under-predicted. If we're below 0, this is an over-prediction. We overestimated. So above 0 is an under-prediction. Below 0 is an over-prediction. And that would make sense because if we look at our graph, this is our actual value up here that's circled, but look where our line predicted it. We're way below. We predicted way less than what it actually is. But also, this residual here is kind of an outlier because it's larger than some of the others, most of the others. So an observation is an outlier if it has a large residual. So that's how we can graphically assess the fit of a line. Now let's talk about numerically assessing the fit of a line. So we're going to need some formulas. The first formula is the total sum of squares, which they say is denoted by SSTO. A lot of your statistics books, like if y'all take statistics again in college for whatever reason, a lot of your books, instead of saying SSTO, will just say SST. So, total sum of squares. Which I guess if you write it this way, that'd be sum of squares total. But still, a lot of your books say SST, not SSTO. And that formula is your individual y's minus your average y. So,
You said that, you use SST, not SSTO, right?
I mean, you can use either one. The book uses SSTO. That's just kind of an odd way of putting it. That's the first time I've ever seen it put that way. A lot of books use SST.
Is it the same thing?
Yeah, they mean the same thing.
Why is it SST and not TSS?
Good question. I think I've actually seen books say it TSS as well. So. Yes, Riley.
Oh, never mind.
So this is y bar is your average y. We just take each individual y, subtract it from the average, and square it. The residual sum of squares, which our book says SS resid. I tend to leave off the azid and just say SSR. That's defined as, essentially the residuals squared. That's really all we're doing. Residual sum of squares, we just square the residuals and add them all up. Now, clearly, if you had a small data set, this wouldn't be too bad. You could do it by hand. Even if you had like 15 data points. Yeah, it'd be a little tedious, but you can still do this by hand. Let's say you had not 15 data points, but 15,000 data points. Do you want to do that by hand? No. Not unless a lot of your data points are zeros. So I still see some writing, so I won't change it. But while y'all are finishing up, a lot of your computer software and even the calculators, depending on what kind of calculator you have, they will actually give you, when you run the regression, the total sum of squares and the residual sum of squares. Yes.
So I got the SSTO, and all that, that big equation is the same thing as the sum of y minus y bar squared. Is that what that's saying?
Yes.
Okay.
And really, this is sloppy notation down here. This should say, these summations should say like I equals 1 to n, and these would be y sub i's. So what this is saying is you take every y, subtract it from the average, and square it, and then add them all up. Yeah, this is just sloppy notation here. Okay, so like I said, usually computation or statistical packages will give it to you, but you can also use the following formulas. So another way to calculate the total sum of squares is to do the sum of all your y's squared minus the sum of the y's where you sum them first and then square everything divided by n. So now we're on page 15. Or for the residual sum of squares, you would have to use your A and B from your regression line to get that. So you could compute them. If you didn't want to do the formulas we just gave, you could use these formulas to get them. But they would give you the same answer.
A lot of stuff.
One thing I will say though is if you're dual credit, we just answered number 1 on the homework I just gave you.
Almost work.
What's that? Where we wrote the first formula for total sum of squares.
Oh, that's a few.
Yep. Not up here, but on the previous slide, that first formula that we did for SST.
Okay.
I just answered number 1, so you're a quarter of the way through the assignment. Okay, so these are all great and all, but what are they used for? Well, they're used to get the coefficient of determination, R squared. The R squared is computed as 1 minus the residual sum of squares divided by the total sum of squares.
Don't they give you this in the linear regression?
They do. They do give this to you, yes. So R squared, I'm kind of getting ahead here on the notes. I'm just giving y'all time to get this written down. The coefficient of determination, which we're calling R squared, is the proportion of variation in Y that's attributed to the relationship between X and Y. The linear relationship between X and Y. So it's how well the model is performing. What else do we know of, though, that uses the letter R? Any ideas?
Not using. I forgot.
The correlation coefficient.
That one.
All R squared is the correlation squared. So if you can find the correlation, square it, and you get the coefficient of determination. So like on dual credit, on 2 and 3, all they give you are the correlation. So on that first part where it asks you to find the coefficient of determination, all you have to do is just square the correlation, and then boom, there's your answer. Square what they give you, and you get your answer. Okay, so how do we interpret it? When asked to interpret R squared, you'll need to use the following template. They say formula statement. We call these templates. So this is your template, especially if you're AP. And even dual credit uses this template. You'll use it for 2 and 3. This is essentially part B. Blank percent of the variation in your Y variable can be attributed to the approximate linear relationship between the X and the Y. Now, here's my little 2 cents about this equation as far as AP goes. Please actually write what the X and Y variables are. I was grading that assignment from Monday, that slope and intercept assignment, And several people said, M is the slope. This is how much X, this is how much Y increases when X goes up by 1. You just give me the definition of slope. You didn't even put it in the context of the problem. So make sure you put it in context. The context comes by putting in what the Y variable actually is and what the X variable actually is. Does that make sense? Okay, so we're going to go back to the mouse data. I'm not going to have y'all plug it in to the calculator back into L1 and L2. We don't need that for now. We're going to do this because this is now more algebraic than anything. So let's suppose we didn't know the X values. All we knew was Y. All we knew was Y. So don't literally cross it out on your paper. Maybe just cover it up for a second. Cover up the X's. What distance would you expect the deer mice to travel? Like if you had to tell me a number, what number would you tell me that you expect them to travel? Well, what would that number be called, I guess, is what I'm asking. It wouldn't be X. It would be Y bar. What's Y bar mean? It's the average Y value. So, I don't know who's the quickest typer on the calculator, but someone who's quick, try to calculate the average for us, please. The average Y's. And whenever you get the answer, let's hear it to 3 decimal places. That sounds did you do the average Y's or the average X's? 15.938, that's right. Okay, so I guess I have to look that up here. Okay, so what they did on the next page is they gave you, well, make sure you write down the average. They didn't give you that. But they gave you a graph where the average is plotted on it. Oh, no, they didn't plot it. Let's plot it up on the screen, though. What is this graph? Actually, I think the wrong graph is in your notes. That's what I think. Yeah, the wrong graph is in your notes, but really, you don't even need the graph the way we're about to do it. You can, or you can just ignore it. It's the wrong graph. Okay, so let's find the total amount of variation in the distance traveled. And they give you a hint. And then I give you the formula. Find the sum of squares deviations. So we're finding the total sum of squares. So we're going to take every single y, subtract the mean from it, and square it. So I'm going to save y'all that calculation unless you can just really type quick. What this would look like expanded would be 0. So back. 0 minus 15.938 squared plus 6.13 minus 15.938 squared. And we just keep doing this all the way through till we get to our last data point. 30.65 minus 15.938 squared. So we would calculate all of that. I say all of that like it's a lot. It's only what? 9 observations? That's a lot. When we calculate it, we would get 773.95, and then our units would be meters squared because we squared them. So that's what your total sum of squares equals to. And that's what goes in the first blank on page 16. Now I gave y'all space to work the problem. So you can just, this would be good enough for the work, just showing what we showed here. You don't have to write out all 9 sets saying, hey, look, I took the values, subtracted the mean from it, and squared it. You can just do the first 2 plus ... plus the last one. That's enough to tell me that you know what you're doing. Or to tell me that you don't know what you're doing. Okay, now let's suppose that we do know the x values. So we know something about those x's. Our best guess would be then to predict using the least squares regression line. So how much do our observed points differ from this line? Well, what we're doing here is we're just squaring the residuals, which we calculated the residuals on page, what was it? Page 12, we calculated all the residuals. So I'm just going to say residuals. We're getting those from page 12. We're not going to read. It's still on that. It's driving me crazy. This is page 12. That's where we get them from. So, again, if they're already calculated, you can just, yes. Just show me where you're squaring the residuals. So, negative 14.76 squared plus negative 3.10 squared. And we just keep squaring all the residuals until we get to the last one. 8.06 squared. If we add all of those up, all the squared residuals, That would get us
Well, since the residual always equals 0, that means we would never, it only be one number every time. Upper squared.
well, this is the residual. So this is y minus y hat. That's why it's only one number. Because we calculated this value on page 12.
Yes, sir. That's it.
We did that on page 12. So that I'm just pulling these straight from our table. And if we calculated this, we'd get 526.29 meters squared. So now let's use the residual sum of squares and the total sum of squares to find our coefficient of determination, r squared. And this will tell us the percent of the variation that's explained by the line. Let's do that. Let's write our formula. R squared equals 1 minus sum of squares residual over the total sum of squares. And then we just plug in what we have. So 1 minus, let's see, the residual sum of squares is the 26.27. Total sum of squares, 773.95. If we calculate this, we would get approximately 0.320. How can I put this decimal as a percent? What's that? Yeah. 32.0%. This 32% answers our question here. That's the percent explained by the line. Now, if 32% is explained by the line, how much is not explained by the line? 68%. So I'm going to just add a little note here, and this is, we're going to say 68% is unexplained. And due to other factors. So 32 is explained by the line, 68% is unexplained. So what do y'all think? Is this a good model or a bad model? Yeah, it's a bad model. It only explains 32% of the data. That's not too good. So we're not going to have time to interpret the output, but let's go back to that output. I say go back. It's printed right below. There is one more formula we need to write down though, so don't pack up yet. Okay, so on this output, real quick. This is that field, that deer mice example. What does this negative 7.69 tell us? What's this value? This is the y-intercept. What's this 3.23? Slope. What's this 32.0%? R squared. That's what we just found. Also known as this is glitching and it's aggravating me. Coefficient of determination. And then curveball. What's this value? Oh, that was horrible. What's this value? This is our standard deviation. And this is the formula that I want you to write on the top of page 18. So this is the typical amount by which an observation deviates from the least squares line. And that formula is going to be the square root.
Where is it?
This is on the top of page 18. Of the sum of square residuals over n minus 2. So where it talks about standard deviation on the top of page 18. And we barely made it.